So last time we ended with coming up with this notation for a sum. So the two things we ended with last time was we had a nice definition of area, right? It's the sum of these rectangles as the number of rectangles go to infinity with a constant width. So this was a nice definition of area. And we came up with this sigma notation for sums that enables us to condense this expression. So remember also last time we talked about how it didn't matter where you drew your rectangles, like about the heights of the rectangles, as long as they were on the curve, right? So that's what this sample point means, is that so when we started, we talked about left and right rectangle estimation. So that was a specific type of sample point, where the sample point for the left approximation was the leftmost point of the width interval, and for right approximation, the sample point was the rightmost. For example, midpoint, you would choose the sample point would be right in the middle. So we found out that since the left approximation was always, since any sample point approximation is always sandwiched in between the left and the right, and since we know that these two go to the same answer, that means that by the squeeze theorem, sample point area must also go limit to the same value. It's by squeeze theorem. So to finish talking about so we're very close to the definition of the integral. We just need one more little thing to allow us to be very general. Is this question down here? It's an important question. It's good to think about it before seeing the answer. So we've just established that length does not matter, as long as the length is on the curve. It's defined for a point on the curve. So my question for you is that, so this whole time we've been talking about uniform width, right? You're dividing the rectangle, or dividing the interval into these even intervals. B minus a over n divides the interval into n evenly spaced intervals. So the question is, well, two things. Can you think of a scenario where non-evenly spaced intervals would not work? And can you think of a scenario where it does work? So here's what I'm talking about. Suppose we didn't have this restriction that the width needed to be equal for every rectangle. So maybe for the first rectangle, it's this big, the width. The second rectangle could be this big for the width. The third rectangle would be here, and then here. So maybe our area approximation would look like this. Something like that. For left endpoint, for example. Right? Do you see how the widths are different? So this is different than what we had been talking about with equal widths. So now let's take the number of rectangles to infinity. Can someone tell me if this will give the actual area, precise area? If the widths do not need to be the same, would I still get the exact area? So there's kind of two answers to this. So what's a scenario where you do not get the same area? So do not get the area. Can you think of a scenario? Like imagine you have these infinite number of rectangles, but they have different widths. Anyone have a thought? Well, let's think about it. What was so special about the evenly width scenario? Even width scenario. Someone say like why it goes to the actual area. So if I have these even widths, so they're all evenly spaced, same width. So why is that one okay? Like kind of give just like an intuitive explanation why. You don't have to go through the whole proof. But like, why do you think that's okay if they're evenly spaced? Remember, the number of rectangles goes to infinity. Can you explain what you mean by that? Turn even widths into a summation? How about like more like intuitive, like less about like the actual math, like with the squeeze theorem and stuff. Like intuitively, why do you think that would give you the actual area? Like, what do you imagine that's going on when you're taking the number of rectangles to infinity? So like, what's happening as you go to infinity? As you keep on increasing rectangles, what happens? Yeah. So instead of saying reduce to single point, say the width goes to 0, right? So if the width goes to 0, then it's kind of like they're single points. So then you just get everything that's under the curve. So that's the idea. Like since the width is going to 0, there's not much you can deviate from the curve, right? As the width shrink, this error is getting smaller and smaller because the width is getting smaller and smaller. So, can you think of a scenario where you have unequal widths? So then what's the problem with unequal widths? So if we just had the uniform width, as you take n to infinity, the w goes to 0, right? That's because it's b minus a over n. And then n goes to infinity. Can you guarantee that the widths go to 0 if you just let the rectangles be whatever? Why or why not? Like, what do you think would need to happen if you do actually get the area with unequal widths? So you never reach 0, right? You're getting... So they could all reach 0 eventually, right? Remember, limit doesn't mean you actually get there, right? You're getting closer and closer. So that's actually the condition for it, where you actually get the area, is that all widths go to 0. All widths limit to 0. They don't have to be the same. But the idea is that all widths need to limit to 0. So that's where this is equal. So you can have different widths. But as you increase to infinity, all you want to say is that all the widths need to limit to 0. So another way of saying that is that the maximum width must go to 0. Does that make sense? Remember, you never actually hit 0. You get like really small. But the idea is that as n goes to infinity, right? The limit of all these widths must go to 0. And in particular, the way to say that is that the maximum of all widths for any point in time in n, the maximum has to limit to 0. Does that make sense? So what is the maximum here? The W1, right? So if I take, so at any point in time, if I look at the new W1, or the new maximum, that set of maximum widths, that set needs to go to 0. So what happens? What's a scenario where that doesn't work? Well, I mean, you can just think of a really absurd one. Suppose that's your width 1, right? And then the rest of your widths can go off to infinity. And then you get the full area, a nice area here. But then this one is just here. You see what I mean? Like there's a width out there that is not going to 0. Even though the rest of them are going to 0, and this is still infinity rectangles, right? Still n is going to infinity. But you have one that's just stuck at this width. So even though the number of rectangles is going to infinity, you're not getting the actual area. So that's why you need to have this restriction that all widths need to go to 0. So like if max width does not go to 0, you're not guaranteed the area. Does that make sense? So intuitively, right? You can think of this kind of absurd example where one rectangle approximation is just sitting at, really a bad error. And the rest of them can still go to infinity. But you can imagine if all widths go to 0, they could be unequal. Remember, limit does not mean actual value. So technically, right, like the width can never be 0 because it would not calculate an area, right? Remember, these are like really small widths. But the limit of all these widths need to be 0. So just a little, does that make sense? Okay, I'm going to assume it does. Okay, so we can adjust our definition of area. So we'll call delta xi star, for obvious reasons, the width of the ith interval. So it's no longer uniform. So why delta x? Because it's the difference in the x values, which is width, right? Difference in the x values, right? If the width is AB, delta x would be B minus A. It's just like normal. So here's the proper definition of area. So it's allowing for these different widths. It's the limit as n goes to infinity of this new width, delta I star. So why the star? Because it can be whatever you want it to be. They all need to be the same. Of sum from I equals 1 to n of our xi star. So we can bring that delta x inside. Well, it should have been inside to begin with. So there was w here, and then we're bringing w inside. So we have I equals 1 to n, f of xi star, and delta xi star. So this is length, and this is width of that rectangle. And the only thing we need to say is that the maximum of delta xi star goes to 0. So this is the area under the curve. Okay, so any questions on that statement? So we can't get any better than that, right? We have lengths that can be whatever, and widths that can be whatever, right? The only condition we have on the widths is that if you take the biggest of them at any point in time, that set must limit to 0. Okay, so questions on that? All right. So now so imagine like if you're, discovering this for the first time, you probably don't want to write that out every single time when you want to find the area underneath the curve. So what you do is you want to condense this into a nice notation. So we're going to call the area under the curve f of x from A to B will be called the integral of f of x evaluated from A to B. So we're not really doing anything special here. We're just coming up with a new notation. It's called the integral. So the integral from A to B of the function f of x. And we're going to put a dx here for some reason. I won't say right now. And this is going to be equal to, just by definition, what we just said. So this is what the integral is. Okay, so any questions on the definition of the integral? Again, there's nothing new here. So something you can think about, dx takes the place of width. Notice in our notation of differentials back in the day, delta x was very close to dx, or rather delta x was equal to dx. But if we're saying that, if we're allowing for different types of delta xi star is going to be very close to dx. Our f of x takes place of the length. Yeah, so then it's of the whole curve, and we're kind of turning this kind of, you can think of this as a discrete form of the area, because this is over integers, and then when I say f of x is kind of like, I'm talking about the whole thing at the continuous function as a whole. So there's like kind of more infinity going on here than here, but they're the same exact value. Okay, but there's nothing special here. This is just turning all of this into a condensed expression. Okay, so let's do an example of finding an integral. Please stop me if you have questions. Let's evaluate the integral from 1 to 2 of x squared plus x plus 1. Okay, so what is this? Well, it's defined as the limit as n goes to infinity of the sum from I equals 1 to n of, I'm going to put f of x here, f of xi star delta xi star. Okay, so remember we established that these don't matter, the sample point and width. So why don't we just choose, let's do left approximation. Actually, right is probably easier. Let's choose right approximation and uniform width. Okay, someone tell me what the width is. What is delta x? So I'm evaluating the function x squared, the area under the curve x squared plus x plus 1 from 1 to 2. So if I want uniform width, because when you're actually calculating, right, you probably want uniform width. Yes, 2 minus 1 over n, which is 1 over n. Okay, so if I want to do right approximation, what should my f of x1 be? So what's the first length? So first rectangle length. So look at the, so 1 over n is when we start at 0, right? But we're starting at a different point now. Starting at 1. So what would the first rectangle be? Yes, 1 plus 1 over n. So f of 1 plus 1 over n. Okay, so what would the second one be? 1 plus 2 over n. What is the last interval? What is the last length? One plus n over n, or 2. Okay, so what do we have here? We have the limit as n goes to infinity of 1 over n, which is our delta x. Then we have f of 1 plus 1 over n plus f of 2 plus, or so 1 plus 2 over n plus f of 2. Okay, question. Can we make this at all easier? That's a lot of stuff to plug in there. Can you think of a way to make this easier? Instead of having to plug 1 plus 1 over n into x squared plus x plus 1, can you use some rules of sums to make this easier? I'll give a hint. Oops. So I'm writing it this way. what's f of xi? It's xi squared plus xi plus 1. So since our delta x's are the same, we can distribute it in. So we have xi squared delta x plus xi delta x plus 1 delta x. Okay, how can you make this easier? So instead of plugging in what we just established, the 1 plus 1 over n stuff, into the whole thing, xi squared plus xi plus 1, why don't you do this? Why don't you just split up the sum? Would you agree it's probably easier to check individually? And that was a rule we had for the sum, right? If you have a sum of sums, you can just split up. Does that make sense? So now when you plug in, you can just take it piece by piece. So let's do this one. So we have 1 over n, and then we have, what did we have? 1 plus 1 over n squared, plus 1 plus 2 over n squared, 1 plus n over n squared. Everyone see what I'm doing? I'm splitting up the sum into chunks that we can take care of individually. Okay, so let's make this look nicer. N plus 1 over n squared plus n plus 2 over n squared, and n plus, what is this? No, 2n, no, yes, 2n over n squared. So we can take out that n squared and get 1 over n cubed, and then n plus 1 squared, n plus 2 squared, 2n squared. Uh-oh, I don't have a formula for that. Right? What was the formula we do know? It's this one, right? 1 plus n squared plus, no, 1 plus 2 squared plus 3 squared plus 4 squared n squared. We have that formula as n plus 1, 2n plus 1 over 6, right? But this sum of squares does not start at 1. Anyone have an idea how you can get around that? How about we do this? What if we take the sum from I equals 1 to 2n of I squared? Would you agree that that includes this sum? This sum exists in here, right? Would you agree with that? If I sum up all the squares from 1 to 2n, this part is inside. Okay, so that's in here, right? So from I equals n plus 1 to 2n of I squared, this is what we want, right? This is our sum. So what's missing? If we have our sum here, and we know this formula, what's missing? One to n, yeah. So these things we know. So in general, this is a rule for splitting up sums. You can split it up over the index, right? And this is pretty much associativity. Right? You can group it however you want it, right? You have the sum from 1 to 2n. You can split it up from 1 to n, and then n plus 1 to 2n. Okay, so let's do it. So if you plug 2n into this formula, we have 2n plus 1, 4n plus 1 over 6 is equal to n plus 1, 2n plus 1 over 6, plus our sum. So all we need to do is solve for s. So one thing we can do, can you think of a way to make this easier to solve? Instead of combining fractions and doing all that? What's a good math trick? Right, that's one thing you can do. You can get rid of the 6's by multiplying both sides by 6. Is there anything else you can do? There's another common term. Once we have a 2n plus 1 and a 2n plus 1. And we also have an n and an n. So we can turn this into 2 times 4n plus 1 is equal to n plus 1 plus 6s over n 2n plus 1. So look how nice that was. I don't have to really do anything else, right? The only distribution I have is 2 times that. So it's 8n plus 2 is equal to n plus 1 plus 6s over n 2n plus 1. It's a nice computation trick. So what is that? 7n plus 1 is equal to 6s over n 2n plus 1. So now we can solve for s. So n 2n plus 1, 7n plus 1 over 6 is equal to s. Okay, everyone's that little trick? So notice that if you subtracted and combined fractions, you'd have a lot of distribution to do. Or, I mean, you could still factor, but I think this is a little bit easier. Okay, so that's our s. So all of this was this expression here. So we have our area just of that first term of xi squared delta xi, or delta x, because it's the same, equals limit. And then we had a 1 over n for your delta x, and then we just found out what the sum was. n 2n plus 1, 7n plus 1 over 6. Okay. Any questions on that? So if you don't start from 0, right, if you start somewhere like at 1, for example, you have to, do a little trick to get the term you want. So you can start from 1 to 2n, as you might, which would have been nicer. You can subtract it with the 1 to n term. Okay, so now we just solve this limit. And what is the limit? What's the limit? Oops. What happened? Oh, this is an n cubed. So it's 6n squared. Because we factored out a 1 over n squared, right? Yes, 14 over 6, or 7/3. Okay, cool. So our other term, which I won't do the whole thing, was I equals 1 to n of xi delta x. Let's just set it up, though. This one's not as bad because there's no squaring, but our delta x was 1 over n, and then we do the same thing, 1 plus 1 over n, plus 1 plus 2 over n, and 1 plus n over n. So, of course, there's a limit here. So 1 over n, and then we can turn this into n plus 1 over n, plus n plus 2 over n, n plus, 2n over n. So we have 1 over n squared, and then n plus 1, n plus 2, and 2n. Might as well actually do it. So what is this term? Same thing. It's the sum. So the sum from 1 to 2n is the sum from I equals 1 to n, and then also n plus 1 to 2n, which is the thing that we want. So our formula for this one, remember, 1 plus 2 plus up to n was n plus 1 over 2. So if you plug in 2n, you get 2n, 2n plus 1 over 2 equals n plus 1 over 2 plus s. So we do a similar trick. You can multiply both sides by 2 over n. So we get, so if we multiply both sides by 2 over n, we get 2 times 2n plus 1 is equal to n plus 1 plus 2s over n. So we get 4n plus 2 is equal to n plus 1 plus 2s over n. And then we have 3n plus 1 is equal to 2s over n. And finally, 3n plus 1 over 2 is equal to s. Okay. All right, so we have that. So now that we know that, we can plug this expression back into this s expression. So we have the limit as n goes to infinity of the sum from I equals 1 to n of xi delta x is equal to 1 over n squared times this expression we just found out, n 3n plus 1 over 2. Sorry, I forgot a limit. Limit as n goes to infinity. All right, so what is this limit? What is this limit? Three halves, correct. Okay, so we save that. So what was the other thing we saved? 7/3, 3/2, and then finally, this one's actually the easier one. We have limit as n goes to infinity, y equals 1 to n of delta x. What's that? What's the sum from I equals 1 to n of 1 over n? What's that? Remember that? Add 1 over n times. Yeah, there's no I in here, right? So you just add this thing n times. So that's n times 1 over n. So what's that limit? One. Yeah, it's just 1. Okay, so let's put everything together. So the integral from 1 to 2 of x squared plus x plus 1 dx is equal to the limit as n goes to infinity, I equals 1 to n, of xi squared plus xi plus 1, delta x was 1 over n. And we just found this, so we split it up into 3 terms. The x squared term we found was 7/3. The x term was 3/2. And the 1 term was 1. So just solve now. 14 plus 9 plus 6 over 6. So 29 over 6. All right, questions about that? Don't you worry, we'll find a way to make this a lot easier. But as of right now, we have no other tricks than doing the sum. All right, any questions? So by the way, what is this called? Let's just, so this definition of the integral has a name. So this is called, so when we do rectangle approximation, this has a name called a Riemann sum. So a Riemann sum is just let's say the nth Riemann sum. The Riemann sum is just an approximation, and the nth Riemann sum is the approximation of n rectangles. So what is the integral? Is the limit of Riemann sums. It's just a name. Nothing to get hung up about. But what we've been doing are Riemann sums. That's just rectangle approximation. Okay, so now that we have a nice definition of the integral, what we're going to do is come up with a way, and it turns out that the antiderivative plays a role in how to not have to do this every single time when we do integrals. But this is the proper definition of the integral. Remember when we had our proper definition of the derivative, right, with the limit and everything, this is the equivalent proper definition of the integral. Okay, so some things you have to do on homework and quiz and final is given a function and its integral, write out what its Riemann sum would be. But that's what we've been doing. So we'll just be aware of that. Okay, so before we kind of go into how to calculate integrals without doing all the sums, let's think about some properties of integrals and try to use Riemann sums to prove these. So in the end of the day, what's good to remember about integrals is that they're really sums in disguise. So rules that you know about sums will help you with rules about integrals. And some things that are not nice about sums will not be nice about integrals. For example, products. Products of sums are not very nice. It turns out that integrals of products are not very nice. Okay, so here's the first rule that we have. So flipping the integration direction negates the integral. So in other words, like if you integrate right to left, you'll get a negative value. When you do left to right, you get positive. So let's prove this. So what is the right-hand side? Well, the right-hand side is exactly our Riemann sum definition. So it's the limit as n goes to infinity, all that stuff. It's a hassle to write down every single time. It's all of that. Now let's see what happens when we, so what is, what's delta x? If I want to do even width, if I want to do even width intervals, what is delta x? So now delta x is like our w from when we started. What is it? What is w when you want to have even widths? I'm integrating from a to b of f of x dx, and I want to approximate the area using n rectangles. How wide should these rectangles be? And I want them all to be of the same width. This should be instant, because we've done this several times. Yes, b minus a over n. Okay, so now let's do the same thing, but from b to a. Sorry, I forgot the dx. So same deal. But now we have a delta x for this interval. What is delta x of this interval? A minus b over n. So notice my rightmost point is now a. But what's the relationship between a minus b and b minus a? What's the relationship between a minus b and b minus a? What's the relationship between these two numbers? They're just so wildly different that we can't have a relationship between them? Yeah, it's a minus b is the negative of b minus a. So this is not minus, but it's negative. Okay, but -1 is just a number, right? So we can take that outside the sum. Remember, that's our constant rule. And we can take negatives outside of limits, because that's a constant rule for limits. But b minus a over n is just our delta x. Close prime. Okay, but what is that? This is just the integral from a to b. So we're just manipulating rules about sums to prove rules about integrals. Okay, so any questions on that? So when you flip the order of integration, the integral gets negated. It can be very helpful. All right, so questions on that? Okay, let's do another property of integrals. If you have a constant inside the integral, let's see what you can do with that. So remember, if you know about sums, then you know about integrals. What can you do with c inside a sum? Yes, you can factor it out. Every single term in that sum has a c in front of it, so you can factor it out. But the same is true for limits, right? If you have a constant in front of a sum of terms in a limit, you can pull the constant out. But this is just the integral. Okay, any questions on that? So you can see that integrals behave very similarly to how sums behave, which is nice. Okay, another one that's kind of obvious. What do you think this will be? Based on integrals are like sums, what do you think this will be? If you have an integral of a sum, what do you imagine it would be? Based on just how this is going. Yeah, it's an integral of each of them respectively. So let's show that. And again, this is because sums or integrals are just like sums. Okay, so what we can do, since we're choosing a evenly spaced width interval, we can distribute that in. Actually, it doesn't even need to be evenly spaced. Okay, now what can you do? So this is all that. I have a sum of sums, and we know that you can split the sum up. Right, this is just like, also kind of like associativity. Take the sum of each. right? And then this is also a rule of limits. You can split limits up in a sum. This is all assuming that these integrals exist, right? If one of these things didn't exist, you couldn't do this. But this is just the integral and this integral. All right, so that's that. Any questions on that? Things that you would really want to happen, right? These are very nice properties. If this didn't work, this would be kind of hard to work with. Integrals are hard enough to work with. It's nice to have these nice properties. Okay, so here's another nice one. It's kind of intuitive. Let's say I have the integral from a to b. And let's say c is some point in between. Would you agree that this area plus this area is equal to the whole area? That's basic stuff, right? Makes sense, right? So what's the analogous thing in integral? Is that you have the integral from a to b of f of x dx. Then what you can do is integrate it from a to any point in between. Then add that to the other half of it. So you can split up the integral over its integration bounds. So let's think about that. If you have the limit from n to infinity, xi delta x. So okay, let's say we want to say. So notice when we sum from I equals 1 to n, some of the rectangles are inside AC, and some of the rectangles are inside CB. So why don't we split it up? So let's say from I equals 1 to some point in between is, let's say these are rectangles inside AC. And let's say after that, and I might use a different, let's say delta x prime, because you might need to have differently spaced stuff there. So maybe we can even say these could be different. So let these be rectangles in CB. So we're doing a similar trick that we did when we were calculating those areas before, right? We were splitting up the sums. Right? Summing from 1 to n is the same as summing from 1 to some place in between, and then 1 after to n. Everyone agree with that? That's true, right? You can just, it's associativity, right? You can add the first few and then add the last few. I'm going to take that as a yes. All right, so if we take the limit of both, so what I'm going to do is I'm going to change the limit here, because if I want, as n goes to infinity, another thing I want is this delta x, these delta x's to limit to 0. So if the delta x limit to 0, I would want this term to go into infinity. Oops. I would want the number of rectangles in the first term to go to infinity. So imagine as n goes to infinity, I'm also taking k to infinity. So this is just a to c, and this is c to b. I'm not being too careful in the proofs, but just this is the idea of them, right? All right, so all these are kind of things that that should be true about integrals, because they're area. You can split up areas. The area of a sum is the sum of the areas. These are all kind of like obvious things. So let's kind of like do an example where you have to use these rules. Find the sum for the integral from 8 to 10 of f of x dx if the sum from 0 to 8 is 10, and the sum from 0 to 10 is 3. Okay, so what rule are you using here? How do you find this? So I want to find the integral from 8 to 10. But all I know are the integrals from 0 to 10 and 0 to 8. So what do you do? Any thoughts? Which rule do you think you should use of all the ones that we just did? So let's go back. This was the first one we did. If we flip the bounds, it gets negated. The second one we did, you can take out constants. The third one we did, you can split integrals up over a sum. And this is the last one we did, you can split up the bounds of the integral. So which of those 4 rules can you use here? Yeah, split bounds. So what is equal to what? What is the bound that you're splitting up? Of these 3 things, which are you splitting up? Yes, so the integral from 0 to 10, you can split it up from 0 to 8, and then from 8 to 10. So from 0 to 10, it's 3. From 0 to 8, it's 10. So that implies that from 8 to 10, it's negative 7. Okay. So just be aware that those questions can pop up. All right. Any questions on that? Okay. Here's some other properties. And this is all based on area, so it doesn't really need to be proved. But we'll prove it anyway. If f of x is greater than 0 on AB, then what do you think is true about the integral? It's also greater than or equal to 0. Yeah, so doesn't really need to be proven because this is just area. Let's just see how it plays a role in the sum. So in delta x is always going to be positive if you're going from smaller to larger. If a is less than b, delta x is always positive, right? Because your delta x is b minus a over n. And then more importantly is that f of xi is always greater than or equal to 0. Right? So we're summing, right? So if we replace all the, so there's two things going on, right? You have a positive thing here, and if I'm summing. If I replace all the f of x's with 0, does this thing get bigger or smaller? F of x is bigger than 0, and you replace all the f of x's with 0, it gets smaller, right? But this is just 0. This is a sum of zeros. So the integral is bigger than 0. Okay, here's another one. If f of x is greater than or equal to g of x on AB, which integral is bigger? Yeah, f of x is bigger. So why is that? So key thing is here, if I choose the same delta x and I replace, and I'm also using the same approximation. So if I fix my sample point, xi star, and I replace f of xi star with g of xi star, everything else stays the same. Well, since f of xi star is bigger than g of xi star for the same xi star, then the integrals must have this relationship. Okay, not too bad. Okay, here's a cool one. Let's say if you have, here's f, and let's say it's always bigger, or it's always smaller than this line, and it's always bigger than this line. So let's let this line be y equals c, and this one equals y equals d. So f of x is in between d, and it's in between c. What do you think its area, the integral? What do you think is true about the integral? Yeah, so it'll be in between the area of D and C. What is the area of between D and C? What's the area underneath C? Yeah, it's just a rectangle. So it's C, B minus A. What's the area underneath D? It's D, B minus A. So C is in between 1 divided by B minus A So it's interesting, if f is bounded between two numbers, then its integral, when you divide by 1 over b minus a, is also bounded between those same numbers. So it's a cool fact. This will actually say even more about this term later on, maybe next class. Okay, so any questions on that? It's kind of a simple one. All right, and let's do one more property, symmetric properties. Okay, let's say f is even. So it's even symmetric. What do you think this is equal to? If I integrate from negative a to a of an even function, what do you think is true? So let's kind of like sketch that. Doesn't look very even. What do you think is true? Yeah. So this is something that is true. That yeah. So both of those things are true. Integral from a to 0 of f of x dx is going to equal the integral from 0 to a of f of x. Right? Because they're the same on either side of the x-axis. So if these are the same, and this is equal to the splitting up of bounds, and these are the same, it's just twice. 0 to a, not a to 0. Which is twice 0 to a of f of x dx. Okay, right? Since these are the same. Okay. What if f is odd? What do you think is true? About negative a to a. Any thoughts about that one? Integral can be negative. Why is that? If you have the sum of f of xi delta x. This is the definition of the integral. These f of xi's can be negative. Okay, we have that. It's true. Is integral from negative a to 0 of f of x dx should equal the negative of the integral from 0 to a of f of x dx. Okay, so what does that tell you? It's 0. Yeah. Right? Combine both of these things, right? If the integral from negative a to 0 is the negative of the integral from 0 to a, well, if I add both sides by this integral here, I get 0. And they just cancel each other out. And you can set in the sum too. When you plug in negative xi, this is also true for the even. You can do the same thing. F of negative xi, the negative pops out because it's odd. Okay, so what is the integral from negative pi over 4 to pi over 4 of tangent? Zero. Yeah, I don't need to know anything about the integral of tangent. What's integral from negative 1 to 1 of arctan? Zero. What is the integral from negative 100 to 100 of x e to the x squared? Also 0. I don't need to know anything about this is a funny one. I don't need to know anything about a product, integral of a product. I don't need to know anything about e. Right? I know this is an odd function. Then you're done. What's that integral? Dx. It's also 0, right? So, nice little thing to know. If you ever see like bound and negative bound, try looking at the symmetry of the function. Then you can make life a lot easier, especially if it's odd. If it's odd, then it's just 0. You don't need to know anything about the or we don't know what the relationship is yet. You don't need to know anything about the integral of that thing inside. Answer is just 0. Okay, so now let's actually try to find a better way to calculate these integrals without using all that limits and sums. Okay, so this is called the Fundamental Theorem of Calculus. So if it's the fundamental theorem, we think it's pretty important, right? So this is very important. Okay, so I'm going to make a statement. You tell me if you think this makes sense. So I'm going to let g of x be a function of area. And what is it the area of? It's a function of area underneath the curve. F of x between 0 and any value. Do you agree with that? Like that makes sense. So here's f of x. And let's say this is 1 here. G of 1 is going to be this area. So that's g of 1. What's g of 2? G of 2 is going to be this area. It's g of 2. That make sense? So you plug in a number, and it tells you the area between 0 and that number. Is that reasonable to be a function? Anyone think it's not reasonable? Okay. Do you think g is continuous? Let's say if f is continuous, do you think g is continuous? Why not? Don't think so? Yeah. Think about it. Like, think about you're sliding a bar here, and you're moving it around. Ooh, not that much. Oh yeah. This is reals. Yeah, you're not going from 1. So 1.1 is fine here. So as you're sliding this around, right, the area is changing. Maybe over here it'll be negative, right? Because you're doing from like 0 to -1. It's 0 to a number. So this makes sense to be continuous. It's changing continuously as f is changing. What is g? Can you give an expression for g in terms of f of x? Well, we just all this talk about area, right, and integrals. So it's going to be some integral, right? Now, to not be confused with f of x, I'm going to change the variable here. So this doesn't really matter. It's just the same thing. But what will the bounds be? Zero to x, right? So that's understandable, right? So the area function so g is the area function of f. So it measures the area underneath the curve of f. Later we'll say we don't even need to start from 0. If you think about it, right, if you start from anywhere else, g, you could still construct an area function. Okay, big question. What's g prime? It is? Well, how do you know that? F of t? Well, t is just a, don't worry about t. But like, how do you normally do it? If you didn't know any relationship between derivative and integral, how would you figure, what would you do to find g prime of x? Like what is the definition of the derivative? Yeah, be more specific. Like it's something. The limit, yeah. Limit. We're going to do a derivative as a function. So we're going to use the g of x plus h function, the definition. Yeah, we have is the derivative at 0. Okay, so how do you do that for the integral here? Well, you have the limit as h goes to 0 of 1 over h. So how do you plug in x? So notice I put a different variable here. It really means the same thing, but the idea is I want to change x. So it's 0 to x plus h, because this is a function of bounds. So it may be good to note if x is a variable, is a bound variable. Okay, everyone agree that that is the difference quotient? That's the same thing as g prime? Anyone not agree? Cool. What's this? We know what that is based on some rules we have. What rule do you think it would be? Which of our integral rules do you think this would cover? Let me sketch it in case it's not obvious. Yeah, the bound change. So from 0 to x plus h, and if you take away 0 to x, exactly what you're left with is x to x plus h. Not 0. All right, so we really crunch this down. All right, so what is our goal now is, well, we want to calculate what this limit is. Okay, so question. We have f of t. It's continuous. And it's defined on the closed interval x and x plus h. What do you know about continuous functions on a closed interval? What do you know, or what is true about continuous functions on a closed interval? Do you remember that? So this is one of the test questions, quiz questions last time. Talked about this. You had to find something. If you had a continuous function on a closed interval, you had to find some things. Do you remember what those things were? Mins and maxes, yeah. You know a min and max must exist. By what? Do you remember that theorem? Rolle's theorem was for derivatives. This one was the extreme value theorem. So you don't even need to be differentiable for extreme value theorem. Okay, so let's say let u be inside x plus h, where f of u is minimal. And let w be maximal. It could be x and it could be x plus h. So what is this? So like down here, let's say that's the minimum. This is the idea of what we're doing here. And let's say here's the maximum. Okay, so now if f of u is the minimum and f of w is the maximum, do you agree that this is true? Integral from x to x plus h of f of u is less than? Not du. Do you agree that this is true? Not dt. So this is our rule that we had where, like, if you have a function that's bigger than another function, then the area is going to be bigger. This is like y. This is the constant function y equals f of w. So this is the constant function y equals f of u. But we know what these things are, right? What's this? Integral. And what's this integral? So you know them by area. So what is it? How do you find the area underneath those horizontal lines? Yeah, so it's f of u is the height, and the width would be x plus h minus x, which is just h. So we have h x plus h minus. So now if we divide everything by h, we get our expression here. So divide everything by h, we get f of u is in between 1 over h, the thing that we want, right? This is our g prime without the limit. Everyone following? So if I had a limit in here, that would be g prime. Any questions on this? Okay, let's actually do the limit. As h goes to 0, what do you think u and w are going to? Think about how they're defined, u and w. As h goes to 0, what is u and w going to? Yes, u equals w, and what is that value as h goes to 0? It's a specific value. They will be the same, which is definitely true. So what is it? X, yeah. As h goes to 0, these min and maxes are going to the same thing, and it's just f of x. So by squeeze theorem, this whole thing was equal to g prime. We just simplified it. G prime is equal to f of x. So remember, x was the variable of where you're integrating to. So if g of x is equal to the integral from 0 to x of f of t dt. Then the derivative of g is equal to f of x. Okay. All right, so questions on that? So we're squeezing the interval of x and x plus h down to just x. So the max and min is just x. So this is called the Fundamental Theorem of Calculus. So this is step one into making integrals easier. So if f of x, notice all we had was f of x is continuous. We didn't even let it be differentiable. And that's pretty cool. You can have functions that are not differentiable and have an integral. F of x is continuous on AB, and if g of x is equal, and notice that 0 didn't even play a role in this proof, right? 0 didn't even need to be in there. It could have been any number. I just said 0 to kind of make it easier to intuit, but the 0 didn't matter. The derivative is f of x. So we actually just proved also that the area function is differentiable, right? That was the other kind of, we knew it was continuous just by looking at it. We also know it's differentiable, which is pretty neat. Okay, any questions on that? So another way of saying this is that the derivative of the area function is equal to f of x. So there's a direct correspondence between area and derivative, which is pretty neat. It's kind of like they cancel each other out in a way. Okay, let's do an example. Let's say g of x is equal to 1 to x of square root of 1 minus t squared. What's g prime? So remember, yep, that's exactly it. Just square root of 1 minus x squared. Okay, cool. Let's do this one. What if g of x is equal to x to 3 of sine of t squared? What's the derivative? Is this question different than the first question? Are these the same things, or is there anything different about these two questions? Well, first of all, it need to be x, right? Because this is a function of x. But what's different about these two things? Hint, it's actually not sine of t squared or x squared. The bounds are different, right? What happens if we flip the bounds? Yeah, it becomes negative. Yeah, so it's equal to negative of 3 to x sine of t squared dt. and that is negative sine of x squared. So the derivative is that. Okay, so let's do another one. What's that? Is there anything different about this one? What's this? Yeah, the upper bound is 2x. Good, yeah, so it's actually 2 cosine of 4x squared is the derivative. So let's see why. Would you agree that this is true? This is a function, right? It's a function of x. What if we compose this function with 2x? Do you agree that this is the same thing? It's a composition of functions. Right? This is like f of g of x. Yes, no? So what does the chain rule say? It's f prime of g of x times g prime of x. So exactly what you had, Sonia, was, well, what's the derivative of this? Well, it is cosine of plug in g, which is 2x squared, and then multiply it by g prime, which is 2. So that is 2 cosine of 4x squared. So chain rule. So this is just normal derivatives, but we have a wacky function here, right? But this is still just chain rule. But we have this new interesting looking function. What's this? This is way different, right? Any thoughts how to deal with such a thing? So what makes this weird? Why is this any different than the other ones? ln doesn't really matter, right? Notice all these things, all we did was just plug it in, right? So this thing doesn't really matter. But yes, the bounds are interesting. So what's different about this question than the other ones? What about the bounds is different than the other ones? So like, we had this one, not about periodicity, but just like, they both have x's. Both bounds have x, right? That's pretty annoying, right? So we're going to do a neat trick. Yeah, the bottom's not constant, nor is the top, right? If the top was constant, then we could like flip. But they're both not constant. So, well, here's the trick that we can do. Why don't you just split it up? let's have x sine of x, and let's go up to 1. And it doesn't have to be, it could be whatever you want, it could be 0. And then 0 to x. Agree with that? That's something you can do? That's true, right? All I did was split it up. So now you can solve it. So what is the trick here? Is that you can split up the bounds by making up some bound. Remember, the 0 here doesn't really matter, but you want it to be some constant, because that's the whole point of the fundamental theorem of calculus. One of the things needs to be constant, because that's what you're measuring from the area. Okay, so this one is fine. This one is just ln of x plus 1. That's the derivative. So now we're taking the derivative. Okay, but how do you take the derivative of this term? What do you need to be careful of? Yeah, so it's already negative, so flipping it made it negative. We don't need to flip again, right? You don't need to negate again. How do you calculate the derivative? We already took care of the negative. How do you deal with the x sine of x? It's the same thing as the 2x, right? The last problem had a 2x. It's the same thing, you just do chain rule. So first of all, the derivative of the area function is you plug in x sine x plus 1, or x sine x, and then you multiply it using the chain rule by the derivative of x sine x. So the derivative of that is sine plus x cosine. Okay, so that's your answer. ln of x plus 1 minus sine x plus x cosine ln of x sine x plus 1. Okay. Any questions on that? So this one was just the same as the 2x, but the derivative of this required the product rule. All right, so that's all for today. So next time we're going to talk about another fundamental theorem of calculus that is actually not too many lines of proving it, but just to show that the antiderivative can be used to calculate integrals. But we need this to start. Okay, so I'll see you Tuesday. By the way, our last class is Thursday. So next time we're going to go through, finish the fundamental theorem of calculus, and then talk about some derivative techniques. And then we'll end up with calculating the area between curves. So one of the derivative techniques is substitution rule. Essentially turning something into a form that you can integrate. All right, I can stick around for questions if you have them, but I'll stop recording.